Hi again, this is Claudio from expertfea.com with a new live stream regarding finite element analysis with geared assemblies. So let me share my screen. A quick reminder about our website where you can find simulations, tutorials, books, and even live FEA support. Feel free to appeal if you are in need of support or inspiration. So let's firstly see what we have regarding gears on GrabCAD.com. And let's see if we can find something useful. Pretty simple parts, all right. So let's go for differential, yes. As I usually do, I will start modeling the FEA, everything from scratch. So you can see together what are the steps and techniques, the methods for healing the 3D model, for making it suitable for FEA in ANSYS workbench. Let's open some assemblies and we will check them and see if they correspond, if they can help what we need. So yes, I think we kind of have what we need. Another detail, because I have seen on YouTube, yes, okay. Because I've seen on YouTube that some people have analyzed some gears, yes, and they analyzed it in, for example, here in static structure, yes. Of course, given the dilation of these parts, something is completely not right there. We'll use more than 2 gears, yes, and not in static or transient. Look here, as people do. Let's go for explicit dynamics because we have a more complex assembly than 2 gears. We'll not stay with 2 gears. This looks interesting, only it's useless. Look here. Yeah, because it has no parts. Such people and many people like this, they just put something without parts inside and it's useless. It's just for show. Again, useless without any use. Let's download here and see what if it is usable. I've seen something that caught my eye. Is this usable? It looks very nice. Ooh, this is nice. You know what? With the proper joints, I think we would be able to use it in the future. Let me download this just to keep this in mind. And let's click like here. Another differential. This is an assembly, but I would like to see inside. 1 gear, 2 gears. No. 1, 2. I don't see a good profile of the teeth. What do you know? They seem to be good. How do we spell in English the profile? Hypocyclic or evolvent? Yes, I thought maybe the profile of the teeth were not evolvent profile. Let me download this. Like this is an assembly made in 2025. All right. Let's download the entire geometry. And like it. This looks pretty complicated. Oh my God. It looks also very well modeled, very nicely done. It's very nice. These mesh with these, and these with these. Oh my God, it's so nice. Do we have like a section view? Maybe here. Okay, yeah. Oh my God, this looks so nice, and they seem to mesh pretty well. Oh, such a nice model. I will not download it because it's too complex for what we need. Let me also download this one, and I think we should be fine. Download, and like here. Let's open Space Claim, then Workbench. Do we have any message? All right, nothing. Lots of nice models in this domain regarding differential. I like simpler models. This is simple, and what do we have? What have we here? This is the assembly. You know what? Let's download the assembly. Come on, download. All right, so I'm here. Can we open something? Let's see. Differential gear assembly. Is it good or not? Let me see if the teeth are, if they have an evolvent profile. Yes, they seem to have evolvent profile. You know what? What is? So how should it work? We should rotate something. Differential movement. Let's see the input and the output. This is what I'm interested in. Driving, yeah. So we're coming from here, then it rotates this and this shaft. So this means we're going to rotate from here, and it will rotate this one. This is the driving, and this is the driven shaft. Even though here it's a small gear. Here this is just for centering. So the orange one rotates the yellow, and the yellow one rotates both blue gears, which instead afterwards they rotate the green gear, then shaft. All right, so one is like the pair. This pair rotates this pair. So the orange yellow rotates yellow blue, then it rotates blue green. All right, so let's keep this picture in mind. Can I zoom, open link in new window? All right. Open picture. Do we have a picture? Copy image address. Right click. Yes. I'd like to have this in mind. Let's look for, firstly, let's look for interferences. We have something here, but I'm pleasantly surprised that we don't have interferences elsewhere. Let's see what I can do here. Maybe, look, if I orient it here, maybe this gear, draw it downwards. If I draw it downwards, then it will mess up these, yeah? So I will instead move this upwards. Yes. So 1, 2, 3, design, move upwards. Let me select a new anchor, click, and maybe here. Yes, because I would need to have this. 0.5, is it enough? Prepare interference. Yes, a little more, right? Control Z. Anchor again, and I will pull maybe 1 from the keyboard. Prepare interference. Only a very small. 1 point, how much is this interference? 1.2 maybe. Design, move. Let's select this anchor and pull here 0.25 maybe. Prepare interference. Only the smallest. All right, another 0.25, and we should be all right. A new anchor, and upwards 0.25 from the keyboard, and I think we are done. Yeah, no errors found. I don't know if you can see it. Here, no errors found. All right, so we got pretty lucky because we don't have any interference. Maybe we'll solve it faster. What I don't like is this very thin area. I would like somehow to make it wider because it's too thin for my taste. You know what? Let's right-click source, internalize all, file, save as. Let's save it. This is called stream 14. Here, 22. $29. And we will increment, we'll name it V1, all right? 29th of January. Yes, so let's isolate. You understand? I would like to be wider, this face. So let's isolate others, hide others, and let's kind of cut it. Let's see how can we cut it. You know, we have, I'm clicking this X design, sketch mode, and we're going to cut it. I should have oriented somehow like this. Let's see if I can orient. So am I in luck? Let's select these two opposite segments. Design, I will create a plane. Hopefully the plane will cut a tooth or a pair of teeth, but it's not the case. Let's rotate, then move. And how much? 353.5. Oh. 353.6. 353.4. Yeah, this is exactly what I wanted. I am clicking the plane, sketch mode, and let's cut. So to project to sketch segment, maybe this one. Yes. Let's see if I can move it. Can I move it? Yes, I can. And I'd like to cut. It's not such a nice inclination that I have here. So, because I'm not satisfied with this, let's do the opposite. Let's project this. All right. I would like to keep the angle. Yes, something like this. So let me extend what I have here, 180 degrees, and we don't care about this. We will revolve cut this surface that you see here. All right, so I will click the surface, then revolve here, cut here, and if we choose full pull, it will be 360 degrees, all right? Of course, I need to select an axis. So you see, it's now we have something. Yes, it's much wider, and I like it more. Also, I don't like the fact that this is too thin here. I don't like having too fine mesh at this moment. Let's move this. I don't know, 2 millimeters. Is it good? 2 millimeters on this axis. Even 3, why not? We like to have a coarse mesh because we'd like to have very quickly. We'd like to have results very quickly. So we have this. This goes aside. All right. Done. I'm looking for potential too fine mesh. Let's leave it like this. All right, let's make a section view here in order to investigate the holes, but yeah, it's not the correct view. Come on. Yes. So I need to take into account the fact that it's perfectly touching. There is no gap. I need to take this into account. Also here, the shaft is perfectly touching with the hole. Pardon my English. And let's go with these because my intention is to create joint boundary conditions, Revolute joints. Yes, this is why I don't care if it has gaps or not. We can also not, choose not to create the joint, the Revolute joints, because being in explicit dynamics, we have an overall body interaction, a frictionless body interaction overall. So this is nice. We might need to maybe correct it, or maybe let's correct it now. Let's correct it now. What will we do? Will we make the shafts diameters smaller or the holes bigger? What will we do? Let's make the shafts thinner. So this, let's make it 19.9. This, let's make it 12.4. 1, 2, 3. Yeah, this is all. And now, if you pay attention in section view, we have the desired gap. Yes, here we have the desired gap. Here is kind of touching very well. Here also is perfectly touching, and we know there are deviations. Yes, there is no perfect touch. So now I'm wondering what to do. Let's push this to obtain the gap, move, and let's push it to 0.1 from the keyboard. All right, and here, let's move this again with 0.1. And it did the same also on this part because they are mirrored, or they are the same part, let's say. All right, so we have gap here, gap here, gap here. Where else do we need gaps? I think we're nice now. Why didn't it give the correct... when we're selecting two parallel faces in the middle of the distance, it creates a section plane. Yes, this is only possible when we have two parallel planes or faces. So gap, 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 gap here, gap here. This is what we need. Gap here, gap here. Yeah, this needs to be taken into account. All right. Control S to save. Now, do I need the big... let's push it a little here, 30 maybe. In here, I don't need so much. Oh, it's the same. All right, maybe 25. Control S, then I'm thinking about the element size that will be here. Let's hide this. Where will we have small elements? Here. Yeah, let's leave it like this. I kind of wanted maybe. Yeah, let's push this a little. Something like this. 1 millimeter. To have bigger elements here, yes. We don't need to torture ourselves with so fine mesh. Show all, save. All right, so let's go here in ANSYS workbench, drag and drop explicit dynamics, and we will import this geometry. Let me search for it and copy the naming. All right, so let's baptize this stream 14, because tomorrow we will have stream 13. It's a little inverted, but we will survive. Double click. Let's see if we have any question from the audience. No question. Perfect. So I will insert this rotation, then here. The purpose in the end is to rotate these shafts, the green ones. All right. So ANSYS workbench is importing the geometry. This means I can close space claim. Let's close space claim. F7 for zoom extents. And we are here. All right, so we have the default materials. We don't care too much about them. How should we call this? Should we baptize it? Current differential parts. Yes. So have something like this. These are the pinions, pinion shaft, ring gear. Ring, side gears, right axis. Oh my God. Small gear, this is small gear and large gear. This is very easy to, yeah. Propeller, yeah, let's baptize this. I'll call this the ring. This will be small and small and small and small. This should be interesting because they are driven. Yeah. Driven shaft 1, and this is driven shaft 2. Small gear 1 and small gear 2. And the big one is the driving whatever it is. We don't care too much. The naming is not important at this moment. Let's delete the contacts because we are in explicit dynamics. If there is time, we will also do it in static. But I'm proposing you the explicit dynamics approach to see how, hopefully, quick, how easy it is to do it in quick. All right, so can I hope for mesh smoothing low, right click, generate mesh. Yes, it's pretty coarse to say the least. Let's see the default sizing, 18 millimeters. Should we make it, I don't know, maybe 10? Right click, generate mesh. We can stay with such a mesh because it's explicit in static and transient. We have no excuse and we'll get lots of errors. Yeah. Let's change instead of 10, let's maybe make it 8, and we will refine some faces manually. So I would say this is kind of, even though the, oh my God, it's, let's begin refining, you know. So look what I will do. I will go into the geometry and click one face from this gear, one face from this gear, one face from this gear, and so on. Yeah. I selected for all gears a face. And for selection, we're going for limits. Come on. No? You don't want? No? No, it doesn't want. I was hoping that it will go all around to encompass all the teeth, but I would have hoped for a connection. Connection expands the selection to the entire body in principle, but it seems that not today. So yes, let's do it manually. Mesh sizing. For selection filter, let's go to box select, and I will select something like this. This one with control pressed, yes? Let's stay only with these at this moment. And I will go again, single select, with control pressed. I will click, I will unselect the faces that I don't need. I don't need these faces because I don't want to refine the mesh on those faces. I'm thinking also about removing these faces. Should we remove them or not? Let's keep them. All right, before going for a value, let's hide them. And let's refine the mesh for these gears. Only the teeth mesh. Mesh sizing. Again, we're going for the box select cursor. I think you can access it by right-clicking, cursor mode, or something like this. You should be able to find the selection. The selection option. Here with Control pressed, after I click single select, with Control pressed, I will unselect the faces that I don't care about, because I only want to refine the mesh on the teeth, not on the rest of the gear. All right, apply. So here, let's make it, I don't know, maybe 5. Here, because we're talking about these bigger, maybe 6. Let's see. Right-click, generate mesh. So it's nicer, but it's not nice enough. Let's make this 4. Let's make this 5. Right-click, generate mesh. Oh, it's still coarse here. Here is also coarse. Oh my God. Yeah, let's look at the node number. 34,000 nodes. So 3 and 4. It's beginning to look more ornate. Let's look at the big gears. Yeah, there is a small element here, but we don't care too much. You know what? Feel free to refine it. 52,000 nodes. Let's leave it like this at this moment. I said, let's first leave without joints, without Revolute joints. This is the magic of explicit dynamics. Yes, I want to attract beginners to use and to like this domain. Find the basic approach here. All right, but at least we should have a rotation coming from here. Yes, this is the driving shaft or gear. We have multiple ways to rotate it. I promised no joint. Let's see if we can rotate it without any joint. There is the option of remote displacement. Let's see if I can do it. Global coordinate system. Can I assign a coordinate system here on this shaft? Let's see, coordinate system. And here on remote displacement, I will select this coordinate system and tell it to rotate on the y-axis, yes? So I don't need displacement on the y-axis. I can make it 0. Behavior deformable. Yeah, let's leave it rigid. Rotation on the y-axis. How much should we rotate in order to see something? Maybe 180 degrees, maybe, in order to achieve something. Here, by it inserted some values, which were the default values, the default distances from the global coordinate system. So what we will do here, because I assigned my own coordinate system, I will make these values 0 in order to be perfectly located or centered on the coordinate system that I just created. So we will rotate this 180 degrees. And let's assign some other displacements. For example, this shaft I would like not to displace on the z-axis. Also, this shaft I would like not to be displaced on the z-axis. All right, and I will add also this, also these ones. I like to help the solver a little. Because I'd like not to fly away, yes? The minute, in the second they will touch, the moment they are touching. Let's insert here 0.01 and here retain inertia, no. Output controls 100 result number of points. Deformation and stress, right click, switch to automatic mode. Solution, total deformation, we will have velocity, strain and stress. Let's save it and let's solve it together in an initial estimation, an impression of the time it will take to solve. Error reading in the Caire from the simulation. So there is something confusing maybe for the solver. Here. It didn't start from 0. Yeah. We cannot start with the value. You always start with 0. Save. Clear generated data, solve. Again, clear generated data, solve. And how many hours? Around 2 hours, all right? We have high density materials still, yes. We would have had much less if they were plastic gears because of the lower density. All right, so let's apply mass scaling, okay? In order to decrease the solving time. Automatic mass scaling, yes, 0.1 e minus 6 seconds. Maximum par scaling, let's make it here, I don't know, maybe 15. Right click, clear generated data, yes. Save, solve. So instead of 2 hours now, we have 50 minutes and decreasing. Let's accept this, all right? Do we have any question from the audience? No. Let's go here and search for other people's work. Oh, we have audience. So ANSYS, firstly with ANSYS gears, all right? Let's see what other people have done. I will not focus on the 2 gears because, yeah, it's, for example, No legend. It's clearly a static and made with fatigue module. I think it left maybe a no separation contact here. So there is no rotation in reality. It's very primitive, yeah. Let's see if it rotates. This is a playlist. Let's see if it rotates. I'm curious. Does it rotate? Because many users are, look here, this is a bonded contact. If they are using the bonded contact, then we know that the FEA will solve, but with zero use, yes? Look here, bonded contact. And the scale is 15. And yes, we have nothing to learn from here. So, from the playlist. All right, this is also ANSYS, also bonded contact, because why do you use bonded contacts in a lubricated assembly? Why? The friction coefficients should be almost zero. Yeah, it's also bonded contact here. What is the use? Please tell me, what is the use? No separation. Hey, come on. No separation because it does not converge with the frictionless or frictional contact. And that is where people get in trouble. It takes maybe 70 minutes. Let's see, out of curiosity, how it behaves. Ooh, it's kind of promising. Only this gear flies away. So let's somehow restrain it, yes? Can I restrain it from the remote displacement? Can I or not? What will happen if I make these 0 and 0? I'm just asking. I don't have much experience with remote displacement. I usually use joints and simple displacement, but I'm curious what will happen if all displacements will be 0. Clear generated data, yes, and solve. Come on, start solving. All right. So, again, bonded contact, let's see. Yeah, bonded contact, so no separation. So, 0 use. ANSYS transient structure tutorial. Finally, something that looks nice. With joints. One gear is rigid. I know this because of the mesh. Let me show you. So this is the rigid gear, the one from the right. Made in transient. Yeah, nice work. Finally a non-linear contact out of all the bonded and no separation. Per gear simulation 3 years ago. Let's see. Very nice mesh, but yeah, it's so detailed because frictionless contact. This I need to see. 1 second. Why do you use a fixed support? Why? What? Oh, they are fixing one gear. Why? 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 What is this? This also occurs because the scale is exaggerated. So for scale 1, it looks like this, and they will exaggerate the scale. Yeah, it's maybe useful to study the stress in contact, maybe. Mastermind with, yeah, with bonded contacts. Mastermind. This is it's not a good mastermind. This is no. This looks very nice. Oh, look at here at the flow, the stress flow. This looks so nice. Finally something. Mr. Dmitry Kalinin is he's maybe Russian or Ukrainian or something. Something similar. This looks very nice. Does he have? He has also other FEA. Also here. Look here. This is very nice work. Yes, out of all the bonded and no separation contacts. Look here how the stress spots are moving. Come on. It's very nice. So nice. So nice work. So let's see if my assumption with zero displacement works. Oh, yes. Oh, yes. Only it might need, it wants to get out, I think. But let's leave it a little. I think I should have expanded the selection to more faces. I don't know why I forgot to make this zero. I wanted to make everything zero. Because I like what I have, let me duplicate. This is a start, all right? Good starts, promising solutions need to be kept and duplicated. We don't need to over-edit and lose something that was promising in the past. So let's just save it. All right, so do we have any question? Oh, no question from the audience, even though we have, I think, 5 spectators. Once the two tutorials. Let's see if it's bonded again. Play. Yeah, sure, let's bonded or no separation. Look, what is the use of this? All right, I said that I would like to try also with 0 here, all right? And I said maybe let's extend this, all right, here. Should I also extend it here? Why not? Yes. Let's extend more. This is because I'm stubborn at this moment and I promise not to use joints. The joints usually restrict very well the movement. I think it's kind of overkill what I'm doing here. Let's just take a breather and let's solve with what we have now. Does it solve? Yes, it solves. Yeah. So frictionless. What do you know? I'm curious if it will remain frictionless. So nice meshing here, but he's using separate parts to finally mesh here. Yeah, why not? I'm curious if it works. I'm the FEA if it works. Come on, animate. It works, yes. Very nice. Finally, a successful solve. And the stress spreads very nicely, yes. Finally, something useful. Here, because he has these values and they should be 46 megapascals, we should right click and reset the legend, or yes, or adjust to visible. Right click, adjust to visible. Because the legend is not updated to what we see here in the graph. Yeah, and he correlates the theory with the simulation. This is very nice work. Yes, finally we have something to... We can learn something. Planetary gear, how to use constraint equation. What? How many? Only 5 videos? Come on. I published, I don't know, 15, 20 videos in the last month. All right, so where were we? Here. I wanted to see what he or she are doing here. They deleted the contacts and they're using joints. Revolute, yes, it is as it should be. Yes. Something else? Rotational velocity. there is a problem here. You see the teeth are, because there are no contacts. He doesn't have any contacts, so yeah, it does not work. He should have kept, or they should have kept the contacts. No contacts, no. Revolute constraint equation, yes, but it's zero use. Because there is no contact, I think. Let's see. It's you see, it's still no contact. He defined the rotation of the gears, but in reality there is no contact, and you will see. Maybe in the beginning we can see it. Maybe the gears are rigid. Can we see if the gears are rigid? No. I bet the gears are rigid, and he will not show any stress or strain. Only total deformation. After all, it's called rigid dynamics, yes. Finally, he improved something here. Yeah, no contact in rigid dynamics. Okay. So in the end, it works nice in the end. And he repaired everything in the end with those constraint equations. Yeah. Too few simulations. I'm not looking for simulations that I have done. This is explicit dynamics analysis for gears. Oh, finally. Let's see. In explicit dynamics. Remote displacement. What do you know? What? Yeah, no, it makes no sense. So at least here, Mr. Raj applied here the correct coordinate system. And maybe it will rotate, maybe. Let's see. Do you have animations? Or maybe not. Huh? Does it? It rotates, yes. Yes, nice work. 7,000 megapascals because he used the default steel. Yeah, finally, this is good work in explicit dynamics. What is this profile? Come on, what is this? So, how is this FEA behaving? I think I am forced to apply at least a Revolute joint. Please bear with me. Body ground Revolute. So it's rotating about the local z-axis here. And here we're going for joint load, rotation, and tabular time. I promised 180 degrees. And this should be properly centered and fixed, let's say, all right? Only this one, please bear with me. So, ooh, ooh. Let's make the maximum energy error 0. Yes. So, rigid dynamics with Armin Hashemi. Frictionless, yes. Of course. Fixed, why? Why do you... Why it's called fixed if it's Revolute? And he left... What? Ah, he should right-click rename based on definition. Yeah? The contact is good, the joint is good, only he this is not fixed, for example. The first one is not fixed. We can clearly see it's a Revolute. But why is the other one fixed? You know why? To help with the convergence. Joint load actuator. Ah, he made also the other one Revolute. All right, let's see. He should start from 0, or yes, and that's all. It looks nice. Something is not right because here he has one E minus 6 millimeter. So something is not right. Mr. Armin is not showing something. This value should be 20, 30, 50 millimeters. Something is not right. Maybe. Yeah, it looks good in principle, yes. He's doing nice work, only he should right-click rename based on definition. And when he will he do this, then he will have more clear pictures, let's say. But yes, it's a nice work. Let's see also this one. One rigid and one flexible. Yes, this is nice. Finally contact, but I hope he will expand the contact. Not only for 2 teeth, I hope. Is he expand? Yes. Yes. And please, not bonded, please, frictionless. Yes. Very nice. Very coarse mesh. But if it works, why not? He defined the mesh. Yes. Moment. 10 Newton meters. transient. Yeah, very nice. 250 megapascals from the legend. This is a good value. Yeah. Nice work, Mr. Amin. Nice work. He has another one. Let's see what's happening here. Ooh, this looks so nice. It slides away, either this or this. I don't know why. Let's see. Someone is like, this gear is sliding away. So I think it's kind of mandatory to assign those Revolute joints. Let me assign a Revolute joint here. Suppress here, maybe delete them. Here, this will fixate, will properly orient or condition this big gear, this driven ring gear. All right, body ground, Revolute, and we're not doing anything. We don't prescribe anything. This is just for the sake of fixating it in this space. Yes, this is properly restrained, this is properly restrained, and the other gears will be restrained by these supports. And maybe here, let's also assign a Revolute joint. Yes, now we are properly oriented. Yes, we should not tie our hands if we have all the freedom to act. Okay, let's not restrain our freedom. Yes, if we have joints, if we have boundary conditions, let's use them. Any question from them? Oh, no question. What do I know? Silence. So what is here? Add the one with rigid dynamics, and I didn't like the displacement. It's so small. All right. Nevertheless, Mr. Amin should be kept in mind because he's working so much. Look here in the past ones. Also with thermal, he's using COMSOL. Mechanical engineering, specializing in. Oh, he has a website. Free to turn console analysis. This is my website, and let's see the LinkedIn. Mechanical acoustics and vibrations, measures. Iran. Okay, with Isfahan University of Technology. And back after the government cut off the internet. Yes, we know the stations. Oh my god. Yeah. Let's send him an invite if we can. Can I send him an invite? Or only message? Only follow? I don't know. Only follow or how do I invite someone? How do I? Who knows? I'm Harmin Hashim, a mechanical with the master's in the primary. My expertise lies in noise control, thermal analysis, and aeroacoustics with hands-on experience in advanced muffler and metamaterial muffler design. ANSYS at console. Yeah, doing this in a country with so many problems, it's a struggle. And best of luck, Mr. Man. Best of luck. God bless you. Prof. Let's see if we have another bonded contact. Out of curiosity. Do we have proper deformation? Let's see. Yes, finally. Ah, yeah, it's nice, but this gear is very heavily loaded. Oh, this gear should be stiffer, let's say, but it behaves correctly. I think I can make this gear stiffer if I increase the thickness. Let's see. Mesh. Something about the contact? No. Directly for mesh, yes? No contact. Yes, this means the contact will be bonded. Look here. This is a bonded contact. This is so. Use 0. You can take the excuse. You can invent the excuse. Hey, I'm using fatigue and safety factor. This is why I inserted bonded. Come on. We're too old for these excuses. Assist of Spurgers. This is only modeling. Only modeling. Does this rotate? This is a good value for deformation. Frictional contact. Finally, a good simulation from Mr. RJ. Good stress values. Does he have more? He has some Katia, Flint. Yes, nice work. Shaft carrying gear and pulley. Static structure. No, we're not interested. If these are gears, then I'm a Tibetan monk, so judge for yourself. If these are gears, all right. No evolvent. Animate. Ah, it looks like bonded. Yeah, bonded contacts, because in reality, gearbox, yeah, a gear assembly is made by bonded contacts. The gears are welded, you know, in reality. It's sad that they are presenting something like this. Come on. Animate. What? Again, bonded contact. Why? On gear. What do you say gear when you have gears? You have two gears. Oh, this is evolvent. Oh. How does it? Ah. The contact is bonded, yes? Yes, bonded contact. What can we learn from a bonded contact? Come on, Mr. Barata, please evolve, please learn, please. Meshing of gears in ANSYS match. Finally something nice. This looks nice. Gear train. Oh. So this was made 9 years ago. Revolute, yes. Show me the contacts. Ah, no contacts. Ah, maybe it's also rigid dynamics. Let's see. Constraint equations, yes. This rotates, I don't know, it rotates weirdly. The one in the middle, it rotates. According to the common sense, it should rotate also clockwise. Why is rotating counterclockwise the one in the middle? I don't understand. Yeah, nice work. Eight years ago, 9 years ago, then stopped. Gear model, yes. You're doing model when you don't apply any boundary condition, no contact, nothing. Another bonded simulation, yes, another bonded simulation. Why not? Let's see if it works. It works in principle. Does this rotate? Yes, it rotates. I should make this gear stiffer. You know what? We know that it works, yes? So let's make this gear stiffer. And we will achieve a nice animation, nice results, then we will be satisfied. Come on, I interrupted. Save. Let's animate a little. Oh my god. Oh my god. Oh my god. What? So we should apply proper joints. All right, nice try. We know now that we should restrain everything better, yes? So much for improvisation. No question, all right. So let's duplicate. I was reviewing the boundary conditions. Let's name this V2 because I would like to increase the stiffness of that gear. I can also make that gear, the big gear, the ring gear, I can also make it rigid, but let's make it stiffer. Space Cleaner is opening now. How much time we have? 1 hour and a half. All right. Space Cleaner. I said that I will make this stiffer by moving this with 10 maybe? Yes. Let's leave it with 10. All right. Let's also increase here. 3. And I would want this one to go more inside. Something like this. 2.5. Yes. Yeah. Ooh, there is an initial collision here. So let's choose anchor here, and I will move this outwards with 0.5 and two again. It's much stiffer, yes. Upwards to here, I don't need that. Do I need this space? No. And this one, I will move it something like this. All right. So I simplified pretty well. Let's make this chunkier. This with 2. Also this with 2. All right. Yes, everything is solid. Do we have prepared interference? How much should we go outside? Normally we should round these edges. We should apply fillets normally. But this will this would impose some mesh refinements, and we don't feel like doing this. So I'm looking here. Uh, 0.35. Let's see. Prepare interference. All right. Design, move, triple click, anchor here, and 0.25. Prepare interference. Yeah. Anchor here 0.3. Prepare interference. Again 0.3. Anchor here. No areas found. All right. So let's right click, source internalize all. Let me save this as V2. Let's close this or leave it open. Let's leave it open for easier import. It's importing very fast because base claim is left open. This is not the geometry that we want. Come on. Scenario was coordinated the same. So you want to say me that no, it didn't import the correct exit workbench and decide later. The software got confused regarding the files, but we will solve everything, no problem. File has been edited or modified. If you choose yes, changes made. If you choose no, you'll be able to recover your modifier. Do you want to return the project to its last saved state before opening? All right, let's see. Duplicate. It's nice that I saved the model as version 2. here V2, right click, replace geometry, V2. Double click, yes. Come on, this ring gear should be thicker. Also the other ones. But I'm interested mainly in this gear. Come on, import it. Let's see what loads we should apply again. So this is what we need. Coordinate system. Do I need this coordinate system? I don't think I need it. Connections. Let's delete these default connection joints. Also these ones. Also these ones, because they are default fixed joints. Let's group all these joints into one folder. We delete the other folders. This is the one of the joints. This is this joint. This is this joint. All right. This joint can be, you know what? Because we have a contact, let's say between this and this, let's make this joint body-body. And we will select, we have this for one side, and let's have this for the other side. So we'll have the joint between these two. This is regarding this gear, all right? So this gear should have body-body with, let's also select this face, even though maybe it's redundant. We hide it with F9. Click these faces, apply. So right click, show all. We have this joint here. And also we do the same here, yes. Body-body, Revolute. Apply here. Let's hide this and apply here for the other side of the joint. Right click, show all, red and blue. All right. Joint, joint, joint. And here, this is what we need. All right. I would have wanted this to also be, because it's usually encased in a housing, I would also like to have this with the body ground revolute. Yeah, so two joints from ground to ring and from small one to ring here. Yeah, from this one and also this one encased in a housing. And it usually it has a bearing inside the housing or maybe a bushing something. So we have everything we need at this moment. Right click, generate mesh. Let's see if I have the proper selection for the face sizing. Yes, and yes. Joint rotation. Also, yes, we have this. This will also be in a bearing or a bushing inside the housing. All right, save and solve. Please excuse me 1 second. The smartphone is ringing. Yeah, spam from Germany. What do you know? The creativity of some people. Why it's not working? I have this joint here. I have this joint here. I have this joint here. You know what? Let's delete this because I already have this joint here. Then this has no joint. So let's apply body to ground. Yeah, let's suppress this one. Clear generated data, yes. The one that I said it pertains to the housing. Let's delete it. Maybe we have redundant. There is a redundancy here, and I would like to avoid redundancy. Solve. Yes, it works. So it should work in principle. Simulation of the meshing of misaligned gears and impact. Oh. It's made by me, so it should work. And it kind of works. There was a it's a start, 13 years ago. I'm not very proud of this. But it's a start, and it's not bonded, it's not bonded or no separation. So, gears lubrication. Where is the lubrication? Oh, yeah, this looks nice. This looks nice. Screw gear. Mr. Sufyan Ahmad. You know what? Maybe you should change your mail because you're not a student anymore, Sufyan. Nice work. He took inspiration from my work. I have similar FEA done before him. Oh, let's see this here. So what is this? It's not working, man. Friday, it's not working. What? What is this? Come on, it's not working. It's not correct. Rigid dynamics. It seems to be good. It seems to be good. It looks nice. Again, bonded. Again, why? Why? Failure of gears. Failure, you should correct your spelling. Let's see what is here. It looks correct, the meshing. The gears mesh correctly. Yeah, nice work. This is made in Adams. Multiple body dynamics. This is made in Adams, I think. Or in recording. I think it's Adams. McNeil, MSC Adams, or Hexagon Adams, or McNeil Schwendel Corporation Adams. This is, we don't care about abacus. Because it's not friendly towards beginners. Concentric magnetic gears via magnetostatic analysis. Yeah, I don't know what is this, but it looks very nice. And this is how a gear is machined. This is very nice. Yeah, this is how one of the methods to obtain teeth. With a profiled mill, you know, a mill with evolvent profile, and it's machining the gear according to what we need. Yeah, very nice. As I said, these are in the housing, yes. Rack and pinion. Does it work correctly? Let's see. Oh. Why is it flying away? Why? Oh. CUI. Come on. We do have a pretty sudden load, and the end time is very small. Just for fun, let's see if I can assign y to be 0. And again, as we did in the past, displacement x to be 0. And the other ones. I was thinking also this one to make it 0. Yes. These ones, and yeah, in principle they should stay. Why is it? It shouldn't be flying away. So let's solve it. Of course. Because this face is very close to this joint, let's instead select this face. I don't know if it will work. This face is close to this joint. Let's select this face. And also this face. Let's see if we can fool the software. So it works, all right. So yes, it should work in principle. This should be nice. Let's see. Yes, it is nice. So this person kind of copied entirely my one of my tutorials. He also applied the spring that I applied here, so he made a 100% copy of one of my tutorials. Yeah, it works, you know, it works. So I'm happy that it worked for him. Yes, ANSYS tutorials, but Mister, you're putting my FEA. This is my FEA. This one and this one. Come on, professor, what are you doing here? So hush the schmuck. Why do you use other people's work? Okay, this is not mine. Instead, for the thumbnail, he has used my work. Does he have bonded contact? This is my question. Let's see. It looks like bonded contact. Fixed support, yes. Here, fixed support. Why? Why do you have fixed support? Professor, why is there fixed support? Show me the contact. The contact is bonded. Come on, what are you doing? You're copying my work, my pictures for the thumbnail. You're copying and you're showing lousy work. Come on, why do you do this? Did he copy more? Let's see. Ah, yeah. Karad, what? What city is this? In India, Maharashtra, India. Karad. Here, I think he copied CFD from other people. Sorry, professor, you should ask permission or, yeah. You can ask yourself, hey, Claude, you're using geometry from GraphCAD. Yes, but I'm modifying it. I edit it. It's not the same thing that it was in the past. And GraphCAD is for open use, it's no problem. And I also gave a like. I'm curious if the professor gave me a like. Planetary gear logic, years work, yes. This is nice. These guys from CFX Berlin, they're doing extraordinary CFD simulation. Yeah, extraordinary CFD simulation. This is also copied from my first simulation that I published 13 years ago. Model analysis. Yeah, the FEA where you don't need to do anything. It's just solved itself. And what is the purpose of this? This is very nice. This is super. Yeah. Do they have something more? Here they have. Finally, nonlinear fictional contact, yes. Yeah, very nice work. And they're good with animations. So, velocity, pressure. This is the inlet, this is the outlet. Very nice. They are doing extraordinary work. My God. Pixar level animations. Very nice. Nirvana. This is Nirvana. Ah, in Star System. You should check their website. It's extraordinary regarding CFD. This is nice. I collaborated with this person, Sergio. Nice work, yes. So, what have we here? Come on, give me good news, please. It is somehow better. There is also this sliding that I don't like too much. Look here, it gets out. Why do I have this sliding? This is ground, this should not go away. Yeah? So look here. Ah, it does not go away, only here. This is not so stiff, let's say. We have ground here. Mm-hmm. You know what? We already have a frictionless contact here due to the body interaction. So I propose to suppress this body by the Revolute joint. So let me animate. To tell you what is my purpose here. So I said animate. Oh my god. Oh my god. I think I need to engage smoother. It's a sudden shock here, 180 degrees for this 10 milliseconds. It's pretty harsh. Let me duplicate. I'll take a look at my smartphone. Silence, all right. Do we have any sign from the audience? Yes, hello, sir. Hello, Kush. We have a sign. Did I duplicate? So yes, this in principle it should be done with realistic end time. I was kind of anxious to show a very easy approach with explicit dynamics because I didn't want to use the contacts. And in doing so, I have imposed a very small end time. And this affected the stiffness of the entire assembly. What we can do is maybe leave this end time and decrease a little here. Maybe make it 90 degrees. And let's here, let's leave it as it is. But 1 second. Why do we need, because we have a gap, why do we need to have this? We have a gap. We have proper contact here. So let's suppress this Here, I will also want to suppress this. I would like to keep that one, the driving, and this one. Let me assign ground, body to ground Revolute. And everything here will be made due to the so-called contact, which is present here, all bodies frictionless. Now we'll have a smoother engagement because I cut the displacement in half. Let's hope it works. Can I, in order to have a faster solving, let's be a little more generous here. 5 and 4. 51,000. Let's maybe go to 34,000, or how much? Yeah. So save. I would like to have a faster solving once we have a proper behavior. Oh, but the teeth, oh my God. You know what? Let's test them just for a while if they work. 6 minutes is nice. What have we here? Gear damage. Oh my God. This is gear damage. So let's see with this picture, let's see what they achieve. What text, mesh. Let me go somehow here. Model. Why do you need model? Why? What? Come on. What are you doing here? You are showing a gearbox. This gearbox. Lots of slides and an integral with no relation to FEA and no gearbox and no gear. Dude, come on. So another volume of fluid. This is very nice from Mr. Sharik Iqbal. Oh my God, it looks so nice. So nice. Yeah, finally something worth seeing. This is nice. It's one animation for 2 seconds, and he or she created such a big video, but showing only one animation, 2 seconds, repeated again and again. No other pressure, no temperature, no streamlines, no nothing extra. All right, to each his own. One gear. The design, immersed cycloidal gear simulation. Let's see the immersion. Where is the immersion? And results? For ANSYS, yes, but it's not made in ANSYS. Maybe he used ANSYS in the name for views, you know, clickbait. How is this lubrication if what? The teeth have no connection with the liquid. Come on, there should be some surrounding liquid and streams. Come on, what is this? Internal magnetic gear. This is ANSYS, all right. Geometry. Bevel gears. Please tell me you didn't use this. Ah, okay, it looks correct now. ANSYS effects. Yes, I would like to see this. It looks promising. And our simulation, how does it look? Does it look promising? It looks promising. Oh my God, finally something nice. Whew. Finally something nice. Even with this coarse mesh, yes? Let's leave it like this, and yes, I will refine it offline because I'd like to finish the stream in the next minutes, in the next 5 minutes, 10 minutes. Ooh. We have so high stress because I have used the linear stainless steel. So my advice for you is to use, in explicit dynamics, always use nonlinear materials, yes? Let's make here 500. Let's be a little more generous. Yes. Yeah, I've taken it from 0, from scratch. So yeah, it's a nice tendency. I worked for, I don't know, maybe 2 hours. Yeah, 2 hours and something. So for a start, it's nice for a start, you know? It can be optimized? Of course it can be optimized. But this is a start. So I showed that we only need to restrain the driving and the driven. Yeah, these pertaining to the housing and this which comes from the gearbox, engine, clutch, gearbox, yes. And with the explicit dynamics, everything is taken into account, yes. So you can forget about all this because we have contacts. We have proper contacts because I have left some gaps in the holes, shaft and holes, and also with the touching surfaces. Keep this in mind in explicit dynamics. Leave gaps because in reality nothing is 0 over 0. Yes, there are gaps in reality. There are allowances. So in the end, this is a very. I also kind of restricted some faces. Yeah, here and also here. So and apply the smoother rotation. If I'm going here with half, then it will be even nicer distribution of stress, you know. And yes, this is my advice for you, and this is a very easy example. It's a quick example how to do it in explicit dynamics. Most of the people that you have seen today, they tried in static and transient, also rigid dynamics, but only one person or two maybe they approached it with explicit dynamics. Of course, not with this complexity, with 1 or 2 gears, something like this. So this is, I hope you learned something today. Let's also scope for some graphical results for the deformation velocity. Save here. So I would like to leave you with deleting these 4. And I lost the results. No problem. Animation. I can do animate. I can animate the results. And here, worksheet, U vectors, V vectors, the vectors for displacement and velocity, and also, as usual, energy. Do we have some temperature? Let's see. And pressure. Right-click, create user-defined results, evaluate all the results. I asked too much. I asked too much. Let's make here 4.5, and let me solve again. Also, can I use nonlinear steel? Let's see. Let's see also the cost regarding the solving time. Structure steel nonlinear, because I'd like not to have 3000 megapascals, of course. Save and solve. I think the solving will be higher than 15 minutes. Let's see. I want to look at the mesh a little, this mesh. Yeah, it looks nice. Yeah. Let's again learn some more from our colleagues. What is this? Engineer. Another bonded contact. So let's see. Differential gear simulation. And this is recent, Mr. Sarkar. Contact. Why do we have bonded contacts? Why? Mr. Sarkar, what are you doing here? Through scale? Why does it work? It shouldn't work. Let me see. Maybe he's exchanging. I'm looking here at the name bonded. Does he exchange? So he's selecting the faces, yes. Are they bonded? Yes, they stay bonded. Why? 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 Why do they stay bonded? Huh? So maybe he will improve in the future. Finally, one of the contact is frictionless. Which one? He left the name bonded. Why do you right-click rename based on definition? Why? So he has the same. For some years he kept bonded contacts, and for some years he has frictionless contacts. Adjust to touch. This is a good suggestion. Adjust to touch. So it's a mix of something good and something awful. What is this? So he only has contacts for half of the gear. Yeah. Come on. So the FEA is partially correct because he has mixed contacts, bonded and frictionless. I don't see where the bonded is. Look here. This is interference. This is correct. This is interference. This goes through the other one. This is interference because here there is no contact. You remember he selected only a few teeth. Interference, interference. So this FEA needs to be improved. Why did he apply various joint loads when one is enough? Yeah, I hope he will improve. Spring. Good luck, Mr. Sakar. Abhishek Iskar. Created with him in the past. YouTube kind of changed the resolution of the older clips. This is why it's not so good to see. This is nice. Herringbone gears. Yeah, with proper touching, no collision. This is what? Yeah, kinetic energy. Some moment reaction. This is done in transit structure. Oh, so nice, the pressure on the teeth. Yes, how is the FEA going? 5 minutes. Oh, finally, it looks so nice. Oh my God, so nice. Do we have some stress? The stress values should be lower, should be more realistic. Right click, adjust to visible. Look here, 339 megapascals. And we can make here maybe 275, 250. The yield stress, you know? And yes, we have nicer values. Yeah, they look so nice. Let's also apply a strain because I said strain. Can I delete this? No. The strain should look nice. Oh, yes. Why is it after the contact? I don't understand. We will consider it as a bug, you know? It's a glitch. 0.001. Oh, yes. Nevertheless, this spread of the deformation, this deformation pocket, it looks very nice. This software is crazy. ANSYS Rocky Dem Gear Drive. Why is this software crazy? Let's see. We don't know. Why is this software crazy? Dynamic model of gear mesh. Yeah, Mr. Dmitry. Very nice work. How to make helical gears in space crane. What is this? This is helicopter landing gear. This is a landing gear. Okay. Yes. Yeah, this is the tool for machining gears. I don't know what they are doing here, but this is the tool. Yeah, this is the mill. Finally, something nice and useful. This does not look correct. Oh my God! Oh my God! So nice. Cavitation, yes. What is? Oh. So I think we are closing. We're reaching the end of our live stream. 1 minute. What is this? I don't know what it is, but it looks nice. I don't understand this actuator. What is doing? I think maybe it's tensioning the chain because we need tensioning in the chain. Yeah. So Mr. Jamal is maybe tensioning. Nice work. Yes, nice work. I would have liked to see some stress, or maybe he is using rigid dynamics because it's the easiest to model. How can you make such a picture? How? All right, so let's see what results we have. Do we have any closing remarks? No. 43. So at least in the beginning, always use in the beginning, use small scaling. Then, if you can, gradually remove it. 1 second for my smartphone. All right. So let's save this. Yeah, I think I should have it. Yeah, it would have helped to fix one of the shafts, I think. Yes, we would have had a more obvious rotation of these 4 wheels if we fixed one of the shafts. Also, we need a longer rotation, a bigger rotation than the 90 degrees. Strain, stress. Vectors. Yeah. Yes, it's a good start, you know. Internal energy. Not so visible. Here we have something. All right. Temperature, do we have? Yeah, we begin to have some temperature and some pressure. 250. Let's animate this and close the live stream. So thank you for your attention, and yeah, so stay tuned because you will learn many new things and easy things to start your project simulations in ANSYS workbench. So, this was not well placed, but yeah, you have seen the ANSYS screen nevertheless. Thank you. Have a nice day and good luck. Bye-bye.